Solving logs, exponentials. We did a little bit of this at the beginning here in that warm-up activity. We solved an exponential problem. We solved for a variable that was in an exponent by using the natural logarithm. There's a couple different types of ways that we're going to solve exponentials and then logarithmic equations. And I'm just going to sort of show you some of the algebraic techniques here to do this. So it's not going to be super involved, and hopefully you'll be able to do some of the homework that's posted after this. So first thing I'm going to talk about is solving exponentials. And we're just going to go over some basic techniques here. So here's my first example. I want to solve this equation 8 raised to the x equals 2 raised to the x plus 1. Okay. And so here's the technique with something like this. This is the trick. This is the skill. Okay. You want to use this rule basically that says like a raised to, the, hold on, not a. Let's not use a. Let's use x. If I have x raised to the a equals x raised to the b, then I know a must equal b. So the concept here, what I'm trying to do is overall, I want to have the powers have the same base. If I can have the same base that I'm raising some exponent to, then I can just solve for when the exponents equal each other. So when I'm looking at this example here, I want to somehow, in this one, I want to change 8 into something with a base of 2. And so this is almost kind of similar to like when you're simplifying radicals and stuff like that. So I can basically take this and say, well, hey, 8 is actually equal to 2 to the third power. Do we know that? 2 times 2 is 4, times 2 is 8. And so the technique is to change that 8 into 2 to the third power using the fact that these are equivalent statements to each other to rewrite what I had there for a question as 2 to the third power to the x, saying that that equals now 2 to the x plus 1. So I'm using this equivalency and substituting. That's substitution. All right, and then from here, you can clean this up a little bit. You can say this is actually 2 raised to the 3x because you're multiplying, right? And that's going to equal 2 to the x plus 1. And so the whole point of this was to then say, because of this, therefore, 3x must equal x plus 1. And then you can solve. Pretty straightforward, right? Subtract x. You're going to have 2x equals 1 divided by 2 divided by 2. I've solved this. X equals 1/2. And so this is basically, it's a technique algebraically that you can use to solve some things like that. Okay? So hopefully that makes some sense. Changing the bases by using basic properties of numbers and exponents. I don't know how else to describe 8 equals 2 to the third power, knowing that you can rewrite 8 as a base of 2, and then having a common base in solving. But if you can't simplify the bases like that, for example, 5 raised to the x equals 2, and this is like a super basic one, but there's no way for you to rewrite 5 in terms of 2 to a power, unless it's some weird fraction. You can still just use your regular old properties of logarithms to solve. So you can use natural log or you can use log, okay? So here's a disclaimer. You can use log or natural log the key is to just always use one of them. So when one of them. Yeah, one of them. So when I use the natural log to sort of unpack this equation, what I mean by using the same one, you need to, if I want to, basically the technique here is to slap a natural log on both sides like we did at the beginning. But the key here is to just make sure if I'm natural logging the left side, I'm natural logging the right side. The reason why I even want to do this natural log process is because now I can use the property of logs to pull the exponent down in front like we did before. Except before we were solving something that was continuous. So there was a base of e, and we used the rule that the natural log of e to the x equaled x. So I didn't really necessarily need to talk about pulling the exponent down in front. But the concept here is that you would actually say this is x natural log of e, and it just so happens that that's like x times 1 because the natural log of e equals 1. Okay, so anyway, the point here is that I will then take natural log of 5 to the x and rewrite it as x times the natural log of 5. And then we say that that equals the natural log of 2. And then it's divide the natural log of 5 out. Divide the natural log of 5. Now, again, we went through these exercises earlier. It was good, those homework questions people asked, to point out that the natural log of 2 divided by the natural log of 5 is not the natural log of 2 divided by 5. So if I want to figure out what that equals, natural log of 2 divided by the natural log of 5, I'm actually going to type into my calculator natural log 2, close the brackets, divide by natural log 5, and discover that that equals roughly 0.43. I'll call it 0.43, right? So x equals 0.43. Question so far? Two different techniques for solving exponential equations using natural logs to unpack some of that stuff. And so you can always do that to pull exponents down in front. So maybe we'll try another one using this technique of applying a logarithm to both sides. Again, algebraically speaking, we're maintaining the sanctity of our equal sign by natural logging both sides of the equal sign. So again, they have different bases, and there's not really any way for me to change those bases into some sort of a answer that I could be then just solving for the exponents being equivalent. So I am going to, again, use the natural log technique to say that this is I'm going to say natural log of 2 to the 4x minus 1 equals the natural log of 3 to the 1 minus x. And the purpose of doing that is to then take these exponents and drag them down in front so that I can solve the equation. So this would be written as 4x minus 1 times the natural log of 2 equals 1 minus x times the natural log of 3. Seeing what I'm saying? Seeing what I'm saying? And now you have to do a little bit of more intense algebra to solve this. So the technique from here is to distribute the natural logs. Okay, so, and it seems counterintuitive, but you have to distribute the natural logs. I guess I can give you the rest of the game plan here. You have to distribute the natural logs so that you can then group the x's on one side of the equal sign, and then factor out the x's, and then solve by dividing. So let's see if I can just show you that real quick. That's the strategy. So I've first used natural logs to bring exponents down in front. So now I want to distribute this. So this is really going to look like 4x times the natural log of 2 minus the natural log of 2. And this is going to equal the natural log of 3 minus x, the natural log of 3. That is distributing the natural logs. And so now I want to group everything that has an x on it on one side of the equal sign. So I want to add x natural log of 3 to both sides plus x natural log of 3. And so I'm also going to want to add the natural log of 2 to the other side to get rid of it. So that it's, because the natural log of 2 on that side does not have an x associated with it. So in grouping my x values together, I end up on the left side with 4x times the natural log of 2 plus x natural log of 3. And that's equivalent to the natural log of 3 plus the natural log of 2. You dig? And so now I want to factor the x's out. That's the whole point of me doing this. So when I go to factor the x's out on the left side, I can pull the common x in front and be left with 4 natural log of 2 plus the natural log of 3. And that is still equivalent to the natural log of 3 plus the natural log of dos mundos. And so now I solve by dividing everything. So I'm going to divide both sides by 4 ln 2 plus ln 3. And so I can do this because the x has been factored out. It's x times this stuff. So when I divide that stuff out, I'm just left with x. So my answer is going to be whatever I get when I calculate this stuff on the right side here. And sure, there are ways to simplify this, condense it into a fraction with single logarithms. Since I'm adding on the top, I could really say that that's the natural log of 3 times 2. So that's really like the natural log of 6 on top. Same deal on the bottom. I could do, that's actually the natural log of 2 to the 4th power. And so 2 to the 4th power times 3, whatever. I don't need to do all of that stuff out because it's just a little bit intense. So what did I have there? I had, let me throw some brackets up. I had the natural log of 3 plus the natural log of 2. Natural log of 3 plus the natural log of dos. And then I was dividing that by 4 natural log of 2. 4 natural log 2. And that was going to be plus the natural log of 3. Plus the natural log of 3. Bang, bang. Close my bracketitos. Enter. I got 0.463, we'll call it. So this equals roughly 0.463. So that's a lot more intense, solving that one. It's, again, just another tip strategy. This is really just algebra, what was done, from here down. This is how you would solve something algebraically, but you just have to understand like how logs work in order to do that. And so like the natural log is its own separate operator on the numbers, so you have to sort of treat them separately. Basically, it's the whole concept that because logs and exponentials are inverses of each other, you can sort of utilize them to solve these different types of equations. But for this one, we're just going to use properties of logarithms. So here's an example. The natural log of x equals the natural log of y. If we could simplify an equation to look like that, you can then, this is a technique, once you have a situation where this is happening, we could then just say that x equals y, and you can solve normally like you would typically for any other type of equation. So with that in mind, we are going to solve this equation, the natural log of x minus 3 plus the natural log of 2x plus 1 equals 2 times the natural log of x. Okay, and so we basically, we're going to solve this by hopefully getting this to just look like the natural log of something equals the natural log of something, and then simplifying it by, understanding to just do the two things that equal each other. So the first thing you want to do is use your skills to somehow combine this into one logarithm. I want this to be one natural logarithm on that side. And since I'm doing addition, what does that mean, folks? Addition means multiply. So this would be written actually as the natural log of, if you can imagine all my parentheses, x minus 3 times 2x plus 1. And that equals, and okay, so here's another trick. If you have this 2 in front, you can put it back up top as an exponent. So this is really going to be the natural log of x squared once I rewrite it like that. So this is an instance where it's useful to go the other direction instead of pulling the exponent down in front of the natural log, you can put it up into the exponent when you're solving something like this. So now what we need to do, a real quick bit of maths here, little foil action there. What do you say? Little foil kid. X times 2x squared. Sorry, x times 2x squared plus x minus 6x minus 3. You know what I'm saying? Ln x squared. I'm just doing a little cleanup work here. So this is really inside here, 2x squared minus 5x minus 3. We digging that? Yep. And so that's really going to equal x squared. So again, this is my whole point. I have the natural log of some stuff equals the natural log of some stuff. I can just say the stuff equals each other. And so from here, you're solving this just like it's a, regular equation. We all should be able to solve this without me really explaining it, right? Bunch of professional quadratic solvers out there. Subtract x squared. That'll yield me a little x squared minus 5x minus 3 action. And if that equals 0, one might be inclined to use the quadratic formula. So 5 plus or minus the square root of 5 squared is 25 minus 4ac. 4 times 1 times negative 3 is negative 12. And that is all over 2a, which is 2 times 1. Yeah, wunderbar. So 25 and 12 makes 37. So I think I got 5 plus or minus the square root of 37 over 2. Yeah. And so that's 5.5 roughly, or negative 0.5. And I'm rounding those. So anyway, this turns into a quadratic. We're using quadratic formula all of a sudden to solve it. But using this concept up here, and once you condense these into the same sort of logarithm, you can solve using that technique. Now, if you don't necessarily have those sorts of things on each side, you can still solve using logs or natural logs, sort of like we did before, just kind of going in reverse of what we did earlier. So if you were maybe going to try to solve this, you might first think to try to combine the logs together. Combine ln's together. So I might add the natural log of x minus 3 to both sides. Now, you have two of them, right? You don't have to write it as, well, you can write it as the natural log of x minus 3 squared, because that is really what it ends up being, right? But I don't know if that's necessarily going to be the best way to do it. You can write that way, but we might think about this as being 2 natural logs of x minus 3, and that equals 5. So I've combined them together. So again, we could write this as x minus 3 squared if you wanted to, but I think it's easier. I mean, I could show you. This is, again, where we get to the point where we're doing some algebra, and it's like, well, you could solve it this way or you could solve it that way. It doesn't really necessarily matter how you solve it. it's going to be more complicated because you're going to have to get rid of the exponent later on. So it's better to just take that 2 and divide it out of both sides and isolate the natural log. So once you've combined them together, the strategy is to isolate the natural log. And again, or log, depends on log, natural log, same thing, okay? So the strategy is to isolate this. So I'll end up with the natural log of x minus 3 equals 5 halves, okay? And then from here, I'm using this rule that says e to the natural log of x equals x. Similar to what we did at the beginning of this class today, except again, like I'm trying to describe it as the reverse of that. I'm not using, I think at the beginning we used a natural log to cancel out an e power base. Now I'm going to use the e base to cancel out the natural log. So I'm basically going to raise both sides to the e. So just for your own knowledge of this, I'll write it out. This would look like e raised to the natural log of x minus 3 equals e raised to the 5 halves. So this is an algebraically legal move to do, to take two sides of an equal sign and then make them powers to the same base. Because I'm making both sides the same base, it's maintaining the equivalency. And so the whole point of this is that the left side then simplifies into x minus 3. And that's going to equal e to the 5 halves. And so as you can see, I would probably want to add 3. So x equals e to the 5 halves plus 3. And then we can use our calculator to discover what that's going to equal. Second natural log gives me e to the 5 divided by 2. Nice. I have an arrow over. And what was it, plus 3? Yeah, we were plus 3, right? Let's just confirm. Yeah, plus 3. So that is going to give me an answer of 15.2. I'm going to round to 15.2. Bang. So ways to use the properties of logs and natural logs and exponential functions to solve different types of equations, different things that you might be looking at. Okay. So I could do more examples. I could keep going through more of these and show you more techniques. Again, at any point in time when you end up, like I think there was one before this where he showed you how you can use these properties to simplify some things out, but you still end up with a quadratic. We're still going to be possibly using our quadratic skills to solve those sorts of things. It's now adding into that, how do you manipulate exponentials? How do you manipulate logarithms? How they work together with each other to allow you to solve different equations. So those are the notes. Thanks, everybody. I am going to work on stopping my video now. I will post those notes at a later date as well, and we can do some more of these examples if folks are interested in that. Obviously, we didn't cover some of the applications, some of the word problems. We've talked about the applications in 5.3 and sort of how they set up with each other. Now we're just going to be doing some of those where you can actually solve some of these equations on your own. It's carbon 14. This is something you maybe want. Carbon 14 has a half-life of 5,730 years. And so that's just supposed to be something that we're sort of given and that we understand, that we know. And so I'm looking at just an example of a mummy that has lost 49% of its carbon-14. So the question is, how old is a mummy that has lost 49% of its carbon? So this is getting much more of an application of things. And so the concept here, which is interesting thing about it, is that if it has lost If my mummy has lost 49% of its carbon, that means it still has retained 51% of its carbon. You have to sort of think about it that way. So if I've lost 49% of my carbon, I still have 51% of the carbon, which is also to say that m of x, then the amount of carbon that it still has, is 0.51 times c, if you will, whatever the initial amount was. C being like the initial amount of carbon. And so when you're looking at a half-life problem that says something like, I lost 49% of my materials or whatever, you want to think about the flip side. How much is remaining? That means 0.51 is still remaining. So you sort of set your equation up like 0.51 equals, and you could say 0.51 C equals C, but you got to, well, I guess I should write that, but understanding that the C's cancel each other out anyway. So you don't really care about how much it initially had in terms of an actual amount. I want to solve for the time. And I again, we have to know that the half-life is 5,730 years. So we're supposed to set equations up using doing half-life like so, any half-life type of problems. But essentially, when you're looking at this question, what it really boils down to, when you get down to the old brass tacks, it's really just 0.51 equals 0.5 to the t over 5730. And the concept there is that we then know how to solve because we can use logarithms or natural logarithms, whatever floats your boat. So if I slap a natural log on both sides, I can say the natural log of 0.51 equals t divided by 5,730 times the natural log of 0.5. And this is, again, me putting a natural log on the right side of that equation and pulling the exponent down in front. And so from there, hopefully we see we want to divide the natural log of 0.5 out. So you'd have the natural log of 0.51 divided by the natural log of 0.5. And that equals t divided by, 5730, right? 5,730. And then to solve for t, multiply by 5,730. Multiply by. So we're going to have to type that all into the calculator. So I might first do the natural log of 0.51 divided by the natural log of 0.5. That's going to give me some small number-ish, and I'm going to multiply that by 5,730. And that's going to tell me that that thing is natural log of 0.51. Yep, divided by the natural log of 0.5. Yep. And then times that action gives me 5,566.3 maybe. So what did I say? 5,566.3 years old. That's an old mummy. And so I guess that sort of makes sense that it's almost, so if it's lost 49% of its carbon and the half-life, so again, half-life tells you how long it takes for half of the carbon to be gone. If the half-life is 5,700 years, roughly, and it's at 49%, that's pretty darn close to the half-life. So my answer would make sense to be 5,500 years old. Which then, if we think about where we're at right now, right, we're in the year 2000. And so what is 5,560 years old in relation to that? Well, that's going to put that somewhere around 3000 BC, 3500 BC. Yeah. Which makes sense. That checks out. So anyway, that's how a half-life problem would work. I didn't record that, so hopefully people saw it and it makes some bit of sense. I did put some half-life problems on the homework, and basically really what you're just trying to do is use that equation there that I posted up there, this equation, half-life. And understanding of the carbon. Most of the half-life problems are in terms of carbon-14, but some of this is like krypton loses 6.44% of its mass each year. What is the half-life? So in that instance, krypton is losing some percent each year. That's telling you, if time equals 1, how much should be lost. And so you would know time, you would know what the original value is, and you'd actually want to solve for H in that instance. So I can just kind of give you like a basic overview of that. Something loses 6.4% a year, 6.44% per year. So if it loses 6.44%, that means it has maintained what percentage? That means it still has 93.56% of its carbon or whatever, krypton still has that much of its mass after a year. So I would sort of want to set that equation up to look like 0.9356 equals 0.5 to the 1 divided by the half-life, because after 1 year, that's how much is left. That's what it said, each year. So if the year equals 1 and it still has 0.9356 of its mass, you can do your same logarithm techniques there, and you could solve this for H. So manipulating that equation in different ways.